So we continue with the part on machine learning algorithms or basics of machine learning. And what we said is basically that we translate our machine learning problem into an optimization problem, a numerical optimization problem usually. Our goal is not to solve this optimization problem precisely optimally, but rather use techniques that are more practical, more flexible. And by far the most important techniques are the gradient-based techniques. Okay, and sometimes these techniques are not just heuristics, but you can actually prove that they converge, they give you the optimal solution. And the idea is that we maintain solution assignments to our parameters in an iterative way. We start with some model and then we improve it and improve it. And again, this is our loss function. And our improvement step, the place we proceed to is based on gradient computation. Okay, so the basic technique is gradient descent, and it is defined as follows. So we have our loss function, loss of S, the set of training examples, and H theta, our model with the parameters theta. So this is really a function of theta. We denote it as L of theta. The gradient of this function of L is the vector with Q entries, where the ith entry is basically the derivative of L with respect to the parameter theta I. Okay, so in each point, you fix all of the parameters to the current assignment, the current state of the parameters, but you take out one of these, treat it as a variable theta I, and compute the derivative of that function in that point. Okay, so that's the gradient. And then what do? At each iteration, we update theta by subtracting the gradient. Not only the gradient, we multiply the gradient by an eta, which is a positive number, the step size or the learning rate. If it's high, then we make significant changes. If it's low, then more modest changes until some stopping condition is reached. Okay, so this is basically gradient descent. And there are some difficulties with this way of defining gradient descent. First, it may be quite costly. So see what we're doing. At every step, we're basically computing not just the loss with respect to all of the examples, but actually all of the gradients. And when the function is complex or we have lots of training data, that can be quite expensive. Okay, so making this computation many times can be prohibitively expensive, impractical. Okay, so that's one thing, efficiency. And specifically, when you want to use specialized hardware that can do a lot of computation in parallel, like GPUs, that can significantly or considerably or dramatically even accelerate your computation, but GPUs can only store what they can store. So if you have too many examples or your algebraic operation, the derivatives is this is a too big of an operation, it won't fit in the GPU. So you need some flexibility on that. Another issue or another difficulty is with the convergence. And basically, which learning rate should we use? If we use a large eta, then we can get crude jumps and then miss basically our miss out on the good low losses. Okay, or we can get to situations where we are going right and left, all sorts of issues, non-convergence. So you say, okay, use a small eta. But if you use a small eta, then first it can be too slow again. Um, and you can also be stuck in some local minimum and not realize that next to you there is some place where you can, again, dramatically lower your loss function. So we need to have some flexibility, some randomness, some noise there. Okay. Um, one of the issue, or probably the main issue, is that the learning rate eta is fixed no matter where we are in the learning process. So if we are at the beginning, we want to have a high eta and proceed fast. If we are close to the end, then we want to be more modest, more gentle with the eta. So we need some flexibility on that. So what do we do? There are several ways of improving, standard ways of improving gradient descent. The first is the stochastic variance. So stochastic gradient descent, SGD, basically picks a random sample. You do not use all of the data set as not all of the training examples, but only one, xi, yi. And you compute your gradient only with respect to this example, loss xi, yi, h theta. Okay, and that's your gradient. And then you update your eta just based on this gradient. Okay, and you do it many times, and it works. And more realistically, you do it in mini batches. Instead of choosing one example or using all of the set S, you use a random subset B called a batch, okay, a mini batch of S. And again, you compute your loss based only on this batch, and your gradient is based on the loss only on the batch, and you update according to it. Okay, and you can cover all of your batches, and once you do that, it's called an epoch. Okay, and you complete your epoch, and then you can run another epoch, further optimizing, further learning until you're happy. Okay, now probably the most popular variation of SGD is the Adam optimizer that basically further improves or adapts the gradient based on where you are in the learning. So it combines some techniques. I won't get to them and to their intuition, the momentum, and RMS prop techniques. I'll just explain, generally, or I'll just explain what the Adam optimizer is doing. But basically, the idea is to maintain some balance between the fast convergence and stability when you need it, by remembering your past. Okay, moving average, taking some average with the past, but your the longer you go in history, the impact is diminishing. So essentially, at some point you forget. Okay, so this is how it goes. And again, I'm not going to describe the intuition. I just want you to understand how this um, algorithm works. And basically to understand that in the end of the day, what we need is to compute the gradient. Okay, so we maintain three values, M, V, and G, each with an index starting with 0. And T is the update number, the iteration number. And G is the gradient. GT is the gradient of theta at time t, as we computed previously. All right, so what do we do? So M is basically the gradient, GT, but actually some average between the gradient and what previously you maintained, the previous M, okay, based on some beta 1 hyperparameter. You also maintain the square of um, your gradient. Okay, so Vt is the square of the gradient, but again, an average between the average and the current and the previous V. All right, and this uses another hyperparameter beta 2. Yeah. Okay. Now we also um, amplify MT and VT by these beta i's to the power of t. So in time, the amplification diminishes. You can verify that this is what is happening. And then we have this MMV, and from these we compute our change. So it's not directly the gradient GT, but rather this value that we computed. And again, we have a learning rate alpha and another hyperparameter epsilon, and these are common values for these hyperparameters. Okay, so that is to say, this is a very popular technique. We'll see that many papers or many models or architectures or settings use the Adam optimizer. And what I want you to understand from that is basically that, well, in the end of the day, you need to be able to compute the gradient. And that once you compute the gradient, you do something that is more than just copying the gradient, but rather do some analysis that changes in time. That's what's important in the Adam optimizer. Okay, now what are the risks? What are the possible challenges or difficulties with machine learning? So these are underfitting. Well, when you cannot fit really your training examples, or the other extreme where you can fit your training example, say, too well, so well that once you see something that is out of your training set, uh, you do poorly on that. So we cannot generalize. Now, we can view these basically a conventional way of understanding this issue of learning settings, basically, is the bias variance trade-off. Okay, and the idea is that bias tells you how biased your setting is towards the simplistic assumptions that you're making. Now we always make simplistic assumptions. Once we often want to learn some phenomena that are not even expressible, with exact functions. So we make some simplistic assumptions on how we believe that the function looks like, or how a function that mimics reality looks like. Okay, so how biased are we towards the wrong places? Okay, so high bias means that we can poorly fit our example. So that's underfitting. And the other issue is variance, and specifically how sensitive the learning is to the specifics of the samples. And the variance comes from the idea that if you get different training sets, your learned model can be very different. Okay, so you can think of it as your model complexity. If you use a model that is too simple, um, then it has a high bias. Okay, it doesn't know how to fit your training data. And as the model becomes more complex, you can better and better fit your data, and the bias reduces. Uh, On the other hand, if you use a model that is very complex, then again, you hang on to the nuances of your training set, and so your variance becomes high. And as you get more and more simpler, um, your variance goes down. So you want to be in a balance between high complexity and simplicity, such that you get a good generalization, okay, good performance on your general population. That's the idea. Okay, so how do we manage the trade-off? Okay, so if we have an issue of underfitting, we can use more complex models. We can learn more, use additional epochs, and or maybe a better strategy for stochastic gradient descent. And if we are overfitting, then we can use a better or stronger regularization. Um, and you know, maybe we need to control our machine learning development by using better splitting. What is splitting, data splitting? So when we learn a function, we usually split our data, the data that we have for training our function, into three parts: training data, validation data, test data. Okay? Now, everything I taught you so far, or everything we discussed, was applied to the training data. We optimize, we process our function based on the training data. With the validation, you use for operations that are not processing, but rather just validating along the way. So you can say, okay, let me look at several variations of our setup or of our architecture. We can use different hyperparameters, or we can try out different models. Like if our model involves some randomness, then we can learn one model, another model, and so on, and then choose the best. The best based on what? Not on the training set, but rather on the validation set. Okay, and the validation set, again, we didn't see it when we trained. We just validate on top of it and make the best selection. Okay, or performance monitoring. If you want to understand where we are in SGD, for example, or we're close to convergence, then we try it out on the validation data, not the test data. Okay, so this is the validation data. It is a part of our training process, but we do not use it directly for optimizing our function or optimizing the parameters, but rather for validation steps. In the end, we report our results on the test data. Okay, that's what we do. Now, um, you can easily cheat there or get models that poorly generalize if you're overly using your test data. Because think of it, you can have some learning architecture, see how it works on the test data, and realize, okay, this is not exactly the quality that I want. So let me go back and change my learning setup and do something different, and then I get a better quality on the test data, and so on and so forth in these iterations. But basically, what you do is that you're fitting your technique to what happens with the test data. And it might happen to be that you're overfitting to your test data. So another common practice is to use holdout data. Holdout data is a bunch of data that you don't get to see. You get to see only one. So once you're done with your training, you say, okay, let me get a portion of the holdout data and then try out my model on top of it. And then I report the number. Now, if you want to further optimize, further learn, then whatever you've seen in the past from the holdout data, that's invalid anymore. It's not holdout data. You can put it, say, this as a test data or use it somehow somewhere else. Next time you'll use a new portion of the holdout data. So that's a good practice for machine learning. Okay, now, once we have our model, how do we actually evaluate it? What is the number that we report? over the test set or the holdout. So for that, we can use any of the error components of the loss function that we've seen. And uh, mean squared error and so on. There's an important case, and very common, of the binary classifier, especially the threshold-based binary classifier, where the idea is that we want to compare models not just based on how well they classify to true or false or 0 or 1 and so on, but we would like to understand how good our scoring function is, how good the score is. Okay, so we would like to have a better comparison between models. So how do we evaluate the quality of our scoring function? Where in the end, our training set only says, 0 examples and 1 example. So the common technique is use the ROC AUC, area under the curve of the ROC, receiver operating characteristic function. Okay, and we'll see it again and again. So it's a good opportunity to explain what it means. Well, basically, ROC AUC is a number. This is the probability that you succeed in the following experiment. Choose a random yes instance according to the label data. Choose a random no instance according to the label data. Is it the case that your scoring function behaves well? It has a higher score for the yes instance than the no instance. So what is the probability that a randomly chosen yes instance has a score or is ranked higher than a randomly chosen no instance? That's the ROC AUC. Okay, and why is it called like that, ROC AUC? Well, because you can basically interpret it visually in the following sense. You place your 0 instances by decreasing score on the x-axis. For each point, you say, okay, if I use the score of this point, then all of the ones that precede it have a higher score would be rated as positive points, although there are 0 points. So these are false positives. Okay, if you use the score of this point as the threshold. Okay, but this is a possible choice of a threshold. Now, for each point, you mark as the value, a y value, the ratio of true positives, the percentage of the 1 instances that are actually scored above, the threshold, above xi. Okay, this is called the ROC curve. Okay, and then basically the probability, for the ROC AUC is the probability that when we choose a random x and a random y, we actually end up in a point that is under the curve. So that's essentially the amount of area under the curve. That's the idea.